Hi folks, we're going to take a look at 1b from page 140. So here they give us this division of a cubic by a linear expression, and the first thing they want us to do is to find the remainder using the remainder theorem. Okay, so we know that the remainder of a division is given by the polynomial evaluated at, in this case here, b over a, if we have the form ax minus b. So here that means -1 over 3. Okay, so we're just going to evaluate that as -1/3, and that will automatically give us the remainder without doing the full division. All right, so let's do that here. So 12 times -1/3 cubed minus 2 times -1/3 squared plus -1/3 and minus 11. All right. So here it'll stay negative because it's being cubed. So this is 1 over 27. So we have -12 over 27. Here this will become positive. So I end up with minus 2 over 1/3 squared is 9. So minus 2 over 9. This will be minus 1/3 and then minus 11. Okay, so I'll start by simplifying this here. Divide both by 3. So 4 over 9, which is nice because it makes this subtraction easier. So -4 minus 2 is -6 over 9. Okay, and again, I can simplify, which is 2/3, which again makes the second. So in the end, this is actually working out pretty nicely. -2 minus 1 is -3, and -3 over 3 is just -1. So minus 11, -12. So actually turned out to be an integer in the end. All right. So here I was able to determine the remainder without having to actually do the division. All right. Now in part 2, it says perform the division and express the result in quotient form. I'm not too worried about what the form is here, but I want to do the division. Here we know that when we're dividing by a linear expression with a non-1 leading coefficient, well, either we have to do it by long division, or if we do it with synthetic division, we have to manipulate the expression a little bit. Okay, so I'm going to use synthetic division. So I'm going to take 12x cubed minus 2x squared plus x minus 11, okay, divided by 3x plus 1. And the way I get around the fact that this has a non-1 leading coefficient is I factor out a 1/3. All right, so I'm left with 12x cubed minus 2x squared plus x minus 11, all divided by, so if I factor out a 3 from the denominator, x plus 1/3. Okay, and now I have something for which I can use synthetic division. Okay, so I'll do the synthetic division on the side so I don't break up the body of my solution here. So I've got 12, -2, 1, -11, all divided by, and again it's going to be x plus 1/3, so it's going to be -1/3. All right, and let's go ahead and do that. So we bring down the 12. 12 times -1/3 is -4. -2 minus 4, -6. That works out nicely too, because we just have -6 times 1/3. It's just going to be 2. 2 plus 1 is, sorry, I feel like I made a mistake here, -6. 6 times 1/3 is 2. And then 2 plus 1 is 3. And then 3 times -1/3 is -1. And actually that works out perfectly because -1 minus 1 is -12, which is exactly the remainder that we got before. Okay, so you see, I thought I had maybe made a little mistake. Just go back and check it right away. Don't wait till you get to the end. All right, so now what does this tell us? It tells us that this expression inside the bracket is equal to 12x squared minus 6x plus 3 plus -12 over the divisor, which in this case here was x plus 1/3. That's what we actually divided by. But don't forget, you still have that 1/3 on the outside. And now to finish this up, we can distribute this back into the bracket. So here we end up with 4x squared. 1/3 times 6 is 2. So minus 2x, and then 1/3 times 3 is 1 plus 1. Okay, plus -12 over, and now when I multiply this to this denominator portion, 3 times x plus 1/3 brings me back to the 3x plus 1. Okay,
Now, again, I suggest you write down all these steps. Otherwise, there seems to be a tendency to make a mistake when reintroducing this 1/3 back into the polynomial. All right. So again, if all you need is the remainder, you don't need to do the division. You just use the remainder theorem. And if you do need to do the division, remember that if you're dividing by something of the form ax minus b, you have to do this little manipulation in order to be able to use synthetic division. All right, that's it for this one.